Meetups to host, but it's really nice to see everyone again, and welcome to the next season of the new computational linguistics in Quebec consortium meetups, formerly known as Montreal NLP meetups. And it's nice to have three exciting presentations today by speakers from UQAM, CRIM, and AI2. For the first talk is going to be by Ana Maria Di Sciullo, who is a professor at Department of Linguistics and Language Teaching at UQAM, and is going to present internal language and external language and why both matter for NLP. The next presentation is going to be by Francis Charette-Migneaut and Lise Rebout, who are software developer, vision imagery, and NLP advisor respectively at CRIM. And the presentation title is FrVD, a new data set of video clip references, actions in French. And the last presentation is going to be by Tanmay Gupta, who's a research scientist at Allen Institute for Artificial Intelligence. And the presentation title is going to be Towards General Purpose Vision Systems. So without further ado, we would like to move forward with the first presentation. But before we start, as always, I would recommend everyone to turn off your microphones and your cameras during the presentations, and so that everyone can enjoy the talk by the speaker. And the last thing is going to be, please leave your questions for the question period. Each talk is going to be 25 minutes, and it's going to be followed by a 10-minute period for questions. So if you have any questions, it would be great if you can ask it during that period. So without further ado, Ana Maria, the floor is yours.
Well, thank you to the NLP Consortium for this opportunity for me to share my reflection, part of my research, and also part of what I passed through, something that the society used with respect to natural language processing. So let's start with the first slide, which is like the purpose. So language, natural language is a biological organism, right? So all humans develop a language naturally, and the child do so rapidly, but their pet don't. So in order to be able to say something about natural language, which is in effect creative, infinite, one has to assume something about the internal property of the human brain to generate an infinity of expression on the basis of finite means. Now, this internal language is under a subject of inquiry from a very different science, and we want to push forward a model which represent, to the extent to which we understand it, what is the language faculty or internal language, internal and intentional language. The external language is the language which we are exposed to. For example, my speech to you. Okay? So what I want to suggest is that I think about this relation between internal and external language, and I look at the interesting development of AI and machine learning on the one hand, and also interesting development in generative grammar. I think that both I language and E language should contribute to machine intelligence. So I will discuss the core concept in generative natural language and natural language processing and in machine learning, and try to push the idea that further interaction between these two fields of inquiry is interesting to enhance machine intelligence, to know more about what humans do in their brain when they speak and what machine do. Okay, so next slide. So this is the general agenda: natural language processing in machine learning. Then learning theories, there are at least two views of what is learning. And then a natural language and natural language processing in generative grammar. And then natural language in NLP. So let's start by this idea in machine learning that generally natural language are sequences of machine readable units. So words are sequences of characters, sentences are sequences of words, and texts are sequences of sentences. Okay, so so a transformer, for example, is a sequence-to-sequence, as a sequence-to-sequence architecture, takes a sequence as an input and produces a sequence as output. It requires the idea of knowing the position of the elements and at the word level and sentence level. And there's also this mechanism of self-attention that enables the transformer to encode bidirectionally and have a hidden state where the full sequence is seen. So the next slide. So also with respect to the different NLP tasks. So in NLP in computer science is concerned with the interaction between computers and humans. So one of the questions is how to program computer to process and analyze large amount of natural language data. So of course, the problem is huge. We separate it in parts. So we have NLP task, right? So in classification task for words, part of speech, name entity, for sentence, for example, sentiment analysis, spam filters, sentence pair, similarity, entailments. And there's classification task, but also generative task, machine translation, question answering, text summarization. And one aspect where, this system is very successful is language modeling. So predict the next word, for example. So learning is in this framework being exposed to a massive amount of example, but example of a certain kind, in most cases annotated on the basis of human intelligence, right? So, and also in this framework, we have to train a model on the standardized data. And then generally, in an exceptional case, there's linguistic bias that informs the standardization of the data. But generally, the linguistic bias is not part of the learning. And the predictions are made about on the basis of mathematical calculi, statistic probability. So, for example, in neural network, you have this idea of sequence-to-sequence architecture with hidden layer, of course, and has this kind of research was brought about. It was much more sophisticated because the idea of deep neural network and the idea of transformer with all sorts of self-attention and point in the computation where you could see specific subpart of a sequence or all the sequence, right? So there's a fantastic work in that area to be able to, in a sense, overcome what is thought about as problems, NLP problems for machine intelligence, right? So for example, word embedding helped overcome the problem of linking word to their semantics, synonymy, for example, but not polysemy, right? Because polysemy is a much more complex phenomenon, which implies some relation on the meaning of other elements in a configuration where the targeted word is located. So there are languages like BERT and Albert that are mass language modeling to predict, for example, the next sentence, and T5 with multiple task text-to-text transformer trained on massive data, and GPT-3 is referred to as human-like behavior for language modeling tasks, right? State of the art for many NLP tasks. So there is progress, tremendous progress in this area to progress in augmenting the performance of a model and beating the baseline for specific tasks, right? So, okay, so please next step, next slide. So this line of research is closely associated with theories of learning which are associative, at the reference of some there. And this associative theory of learning dominate neurobiological thinking as well as computer science, machine learning, and have been developed to, for data analysis and model building. They're based on the idea that system can learn straight from data, identifying pattern, making decision with minimal human intervention, right? So, so of course, these machines say something about how to use a certain theory to learn, so associative theory of learning, but they say little about the knowledge of language which is part of human genetic endowment. Okay, we're talking about machine, and we want that machine be able to learn in a certain theory of learning. So a theory based on behavior and adaptation to the world, okay, to compute, and does not imply representation of that word to start with. So as opposed to this theory, or different from this theory, there are naturalistic theories of learning. You have some reference there, which dominate the linguistic thinking and computational linguistic as well. And the model is based on the idea of human learn genetically, they are predisposed genetically to learn the language to which they are exposed on the basis of partial evidence, the poverty of the stimulus, in Chomsky's terms. And so the idea is that the brain computes a certain representation of the world and the language that describes it. Okay. And that behavior is informed by that representation. And of course, the representation is generated, must be generated by a recursive function, because language is infinite. Let's see the other slide, please. So also interestingly is that the neuroscience seems to bifurcate with respect to these two theories of what is language in the brain. So there's a trend that's going to the idea that neurons are very important, and the part of the brain which is really important for intelligence, quote unquote, depending on what you mean by intelligence, of course, but it's the neocortex as the locus of intelligence. So it learns a model of the world, it's highly distributed, it's a neural network, reference frames, and so, for example, the 1,000 Brains by Hawking is a general book indicating, in a sense, that there's really a conversion between the progress in machine learning and the progress of what we know about what the brain does when natural language comes out of humans. Okay, so different areas are hypothesized and related to the organs of intelligence. We can go to the next slide now. So in another area, another line of research, the idea that the brain includes sub-areas which we can analyze, and have been a lot of experimental work has shown that specific areas of the brain fire and not others when humans speak. So Bronfman 45 for syntax, for example, and Bronfman 44, sorry, for syntax, and 45 for semantics. And there's other parts for the lexicon. And interestingly, this computational aspect of syntax are most likely to be on the left side of the brain. The production or prosody are most located in the right side of the brain. These are finding of, for example, research of Angela Frederici at the Max Planck Institute in Germany. So, I mean, this line of research suggests that, in fact, natural language is the composition of action that the brain does, which are located in sub-areas of the brain, suggesting that language has specific properties in intelligence, as opposed, for example, or as different as vision or motion. So this is a different kind of neurocognitive research related to the question of what is language and how do we process it by our brains. Please, next sentence, next slide. So as we saw until now, there's apparently divergent views of what are natural language and what is natural language processing by the brain and by computer. So now I will in machine learning. So one is machine learning. The one I want to talk now is generative grammar. So languages are infinite. There's language creativity. A human can, by their free will, decide to express a sentence and capable of, all things being equal, of interpreting it as it is perceived. So there is a history in that science, the science of formal grammar and generative grammar, going back to the 50s with Chomsky's aspect of the theory of syntax, syntactic structure, going forward to the 70s with this idea that there's no phrase structure rule anymore, there's rule schemata, and coming to today's, the modelization of the system for today, the idea that there's only one simple operation which combines two elements recursively. And that's the core property of the language faculty. And other elements are part of third factor reducing complexity. So this is a trend suggesting that, in fact, science should be as simple as possible, because nature has, to understand nature more, you need to have the simplest, or the best theory must be the simplest one that account for the fact. So could you go on the next slide? So this idea that they're unique property to natural language, what would there be? These properties are unique and universal. So the idea that one, it's recursion, the other one is binarity, it's the simplest operation that combines element. The third one is structure dependency, which is important because we will see it has a lot of consequences for the NLP task that we are talking about when we do these computational application, whether in machine learning or in that field. And there's an important relation, the relation of asymmetry, which seems to help to convey the meaning of these structure as we have them. So there's example 7 to 9 show that you can't do whatever you want with linguistic expression. For example, if you want to displace a constituent from the sentence who wonder, who behaved, how, so you can't just move how to the front and make a question. How do you believe who behaved? How do you wonder who behaved? Simpler case, you like John and Mary, you cannot extract a constituent from a coordinate structure, which is a island. So you can't say, who do you like and Mary, or who do you like John and. So another example, a bird that can talk and fly. So you can make a question by displacing one of the auxiliary, but not the other, not the first one, but the one at the end. So you have B and C as a difference. Another example with pronominal anaphora resolution, which we will talk further ahead. Well, a pronoun cannot have an antecedent within a sentence. John likes him. Him cannot be John, but can be co-referential with an element outside of the sentence. But it so happens that structure is determinant and not linear order. So the children that deserve them will receive the awards they desire. The antecedent of they at the end is not the award. And it's not the children, but it's the DP, the nominal constituent, including a sentence, which is the students that deserve them. So this is telling that the understanding of sentence is not based on string linearity, but is based on constituent. So there is a relation between constituents that prevail, in a sense, than the one which is a string linear. Okay. The next slide, please. So, so the naturalistic acquisition of language, effectively, this line of inquiry look at children. They go through a certain number of steps to learn a language, but they're born with the capacity to evolve a language in a short period of time. And the mistake children do while they're maturing this language organ, so to speak, is does not violate the constraint on structure dependency, as the ones that I talked about in very general terms just a few minutes ago. So also, eye tracking experiments show that children recognize functional category very early. So function category are not very much talked about in machine learning or in some NLP kind of model, because the models were directed to lexical element, which are supposed to provide meaning. Yes, they provide a certain meaning, but they provide a lot of ambiguity, because words like, I don't know, any word that you can think about may have more than one meaning. But functional categories like determiner, like the cat, well, the is an existential quantifier, and it scopes over an entity of some type. It doesn't mean many things. Okay, so it shows that Gavaro and Shen shows that children recognize functional category very early with eye tracking, and also recursive structure are produced very early and understood by children later on. So these other experiments suggest that if children have problems identifying the antecedent of a pronoun, for example, it might be the case that other principles reducing complexity are not ready in their development of other properties of the brain than language. Please, the next slide. So another issue that is related is language variation, right? So do we have very many natural language in the world. Are they all singular? Are they all they present differences? And even within the same sentence language, you see differences. So there has to be some rationalization or generalization, a natural generalization that comes with nature. This idea of being a species of a certain sort and have not two identical elements in that species, right? A fern, but you have a garden path for a variety of fern. Eyes, but you have different kind of eyes, for example, in the mammalian realm. So similarly, if language is a natural object, you expect a generic properties of a species or an object and variation, constant variation. So how could that be addressed by the human brain? Perhaps there are clues in terms of choices with respect to the general property of language or and the choices can evolve through time, as we see in the historical development of language, like English, for example. In English, in Shakespearean English, I would say, I think not more, or he loves her not. But in modern English, I do not think, I do not love, etc. So if this approach is taken seriously, there's means to identify the minimal difference between language in terms of lexical differences, and mainly lexical differences associated with functional heads, like negation, for example. So there's a way to approach this question of language diversity and consequently machine translation in such a different perspective, different at least that sentence to sentence mapping, for example. So let's go to the next slide. So this is what I was just telling you about. So machine learning is often seen as sentence alignment. But considering the idea that there's a genetic endowment which is generalized over all language, and which is a part of the part of the brain that is dedicated to language, and then that, of course, language evolves with experience, and then there's law reducing complexity. So there's a lot of work suggesting that phylogenetic variation can be modeled, syntactic variation in word order can be analyzed in a systematic way, and that the diachronic variation can be reduced to third factor reducing complexity. Please, the next slide. So in this line of inquiry, there is parsing also, which is a natural language processing type of task. And I will tell you something about the asymmetry recovering parser I developed in my major collaborative research initiative that I got, in fact, renewed through time. So in the time frame of about 18 years or so. So the idea of a sentence like who saw Mary is not the sequence of who preceding saw preceding Mary, but is analyzed as a sequence of projection, which are asymmetrically related because there's dominance relations between the elements that is different, and there's displacement in elements. So, for example, who in that example is displaced from a position within the verb phrase to the maximal projection, which include the complementizer and the WH word. The passive, for example, Paul was interviewed by Mary, again, displacement and maximal projection, and Mary sees Paul, a simpler sentence. So if the brain is predisposed to generate infinite expression, it's at very little cost if it would generate recursive asymmetrical structure for syntax, for example. So there are these asymmetry between argument, adjuncts, and operators are there syntactically, and they constitute the architecture, in a sense, for the interpretation of these natural language expression. It has consequence for NLP task, as we will see. Please, the next. So, for example, a question answering task. So, for example, the sentence, the professor who knows John was on the news. So if you say who was on the news, it's not John, which is the closest string linear constituent, but in fact, it is the professor that knows John. It's the closest structural constituent. So there is a simplified tree in 15b, where you see that there's a proximity, in fact, adjacence between the DP, which is the nominal constituent, and the VP, which is the verbal constituent. And the NP includes a sentence in which a relative clause, in which the head of the relative clause is displayed. So a machine learning question answering system who would look for the closest constituent would have the wrong result. But if you look at the relation between constituent, you have a better result. Please, the next. So recovering, another aspect which is interesting to consider is the recovery of unpronounced but interpretable constituents. So you not putting aside the displacement of categories for a question, John saw who, or John saw this person, who did John see? Not talking about that, talking about elements that are not the result of displacement, but are not audible or readable, but must be understood. So 16, for example, John wants to study. So this sentence include two sub-sentences, John wants something, and John wants to study something. Sorry. So in that sentence, you have two unpronounced but interpreted category. So the idea of going sequence by sequence of word by word, in effect, miss this interesting capacity of human language to induce most important aspect of the interpretation of linguistic expression, because it's simply not externalized. Another example is there are unpronounced element which, oh, is there a sign that I have to stop talking? Hello? No.
You're like past 3 minutes from the time that was your limit, but don't worry about it. We'll probably, if we don't have much time for question answering, then we'll reduce the time for that.
Thank you. So for example, look at simple example in 18. Let's go there. But when I say let's go there, I imply it's a place. Let's stay here. So here and there are elements, are functional elements that provide hidden meaning, right? So, and these elements will play a role in syntax for the interpretation of the sentence they're part. I'll give example after. When I say, how old is he? He's 2. But we know that what is not said is year old most of the time. Let's meet at 2. 2 o'clock, it's a time value. So functional elements like numbers or locative expressions like here and there include semantics, which is way different from what WordNet gives you, right? Semantics of more what they call substantive category, lexical category, which meaning is different from higher level operator in semantics, which identify number in the nominal domain, number in the verbal domain, place, quantification, and so on, time, etc. So the quantification example, John wrote 2 papers, Mary 3. We know that it's paper, so there must be a relation between 3 papers, paper unexpressed, and papers, right? So a system that recovers these unpronounced but interpreted elements in linguistic expression is also important for pronominal anaphora resolution, for example. Please go to the next one, the next slide. So, and again, other example of the similar ones that I previously discussed, you see the post prevents, again, covariates. They learn more about the virus. The post cannot be the antecedent of they, even though the post is a nominal constituent, and they refer to nominal constituents, right? But these posts prevent people, right? But I'm not saying people, but I understand people against covariates. They, the people, the antecedent of they is an unpronounced category. Similarly, the drugs enable quick recovery. They were at home and on time. These drugs enable people or quick recovery. They, the people, were at on time. Another slide, please. So this idea of being of interest of mine and many others with me, with compositional semantics and the role of a natural language logical operator, which has an implication for natural language processing, natural language understanding. And I give a few examples there, right? So at the word level, that's something that one should, there is evidence for that. There's no perfect synonym, right? There's synsets, from the Princeton School of WordNet, right? There's synset, but there's no perfect synonym. So I can say I spent the whole day walking. Also, I spent the entire, sorry for the typo, day walking, but I cannot say while whole and an entire is similar, you can't say on the whole we agree. You can say on the whole we agree, but not on the entire we agree. So they're not substitutable in the same context with the same meaning. So above the word level, you need compositional semantics, right? Because here is an example with order, but it's really the constituent that has to combine together that gives you the semantic. The funding of research by the government is has not the same truth value or interpretation than the funding of the government by research. So there's scope of natural language operator, like negation and quantifier, like not all the arrow hit the target, just a few did, that's fine. But if I say all the arrow did not hit the target, just a few did, it's weirder. Not many drugs were tested, but just a few. Many drugs were not tested, but just a few is weirder. So the scope of the logical operator, natural language logical operator, there are interesting difference which have consequences for natural language understanding. Under example, so in processing knowledge of natural language, and I mean what we know now, that this knowledge, or what we hypothesize now that this knowledge would be, we would have to include structure dependency. I gave you a garden path variety of example where structure is primary, not linear order. Semantic compositionality has to be put in there. And then this ability to interpret covert constituent, unexpressed one, scope of natural language operator, and other high order functional element. So this kind of research could inform machine learning and other systems by ways of integrating these aspects that we discovered in, in the generative grammar framework, and that would enhance the capacity of the system to deal with not only strings, sequences of sequences, but the meaning, the interpretation of these apparent sequences. So this is all, and I thank you for your attention.
Thank you very much, Professor, for your presentation. It was really exciting. We unfortunately don't have any time for the questions, so I'm not sure. Guillaume, would you recommend adding 4 minutes for questions, or do you recommend moving on to the next speaker?
Yeah, let's if there are questions, maybe 1 or 2, that would be okay.
Okay, sure. So we can have about 4 minutes for the questions, and if you have any questions, you can use the raise hand option, and I'll let you speak. So the raise hand option is in the control panel where you can mute and unmute yourself. There's also a hand sign that you can use to virtually raise your hand.
There's a question in the chat, Essam.
Yeah. Yeah, so Dr. Benju wrote, maybe Dr. Benju wants to ask the question himself.
Sure. So I was, I guess, reacting to some of the things that Ana Maria said or wrote. I think there's a confusion here about what machine learning is about. And the particular models that are up there are not what machine learning is about. And also, the core idea behind deep learning is learning representations, right? So it's been the goal of deep learning, right, to discover representations. Now, there's kind of a bit of research trying to come up with representations that capture the kind of recursive structure that linguists have seen in language, and it's totally fitting within the machine learning framework. Now, we don't know how to do that properly yet, but there's quite a bit of research in that direction. The core difference between the sort of let's say classical ideas of linguistics and the way we think about it in machine learning is not about that. It's about whether we're gonna learn a lot of information from the data, including structure, including maybe the grammatical structure, constituents, and abstract, and not just the lexical elements, by opposition to having linguists essentially handcraft all of that knowledge, which turns out to be difficult, especially when semantics comes in.
Okay, thank you. Can I reply?
Yeah.
Okay, so thank you for your comments. And when I was thinking about saying there's no representation, of course, in my head, there's no representation which is structure dependent in the sense of syntax that I see.
But that's not even true.
Okay,
there are lots of models that have syntactic structure. It's just that it's learned. It's learned.
Yes. So, for example, there is attention point, and there's a lot of work on the idea of having a structure there at the attention point, and have statistical calculus used to learn, these structure, and put them in the representations in the process of deep learning or machine learning. Struct form, for example, is one a recent paper on it, and I'm aware of that. When I was thinking of representation, I mean, a model or a neural network is a representation, right? So, but it's a representation of a certain kind. So I should have stressed the fact that yes, in order to build a system, you have to have a representation and have to define this representation. But I was pointing to the fact that there is a difference between representing sequences, right, linearly or in a certain, the relation between the atoms in the neural net is a kind of representation which is different from the kind of representation of linguistic expression that we use in formal grammar, in generative grammar. So I'm not saying that machine learning does not have representation. I'm saying that the representation are different, but compatible, I think, compatible in the sense that once the machine learning, deep learning is more informed or is willing to take into consideration properties of extended projection, structure, asymmetry, when there will come to this point, I think it will enhance machine intelligence.
I agree.
Yes, was my point. And this is why I think that we need to, there is need to work together, because there are things that this science that have been going on in silo should not be continuing to go in silo, should have interaction, right? That was my point. Thank you.
And by the way, the main conference in deep learning is called International Conference on Learning Representations.
Okay, good. But what kind of representation, right? That's the
all kinds of representation.
No, but I mean from the machine learning view. I think there's a role that
including graphs and sets and trees, right?
Yes,
these are part of the game.
Yes. So luckily now it's happening more than it was before. That's my point. Thank you for your question.
Okay, sure.
Thank you very much. We're quite past the time for the presentation.
Apologize.
Thank you, Dr. Sciullo, for your very exciting talk. We're moving on to the next by Francis Charette-Migneaut and Lise Rebout from CRIM, who are going to present FrVD, a new dataset of video clip references, video descriptions, and actions in French for deep learning. So without further ado, the floor is yours.
Hi, can you hear me?
Yes.
Yep. Sorry, so I don't think I share the right screen, but I can't.
Yeah, we can see your screen fine.
Which one can you see?
The one with the slides?
Is it the presentation?
Yeah. Yes, exactly.
It's just not in full screen.
So I'm Lise Rebout, and I'm here with my colleague Francis Charette-Migneaut, and we'll present you today FrVD, a new data set of video clip references, video descriptions, and actions in French for deep learning. So we both work at CRIM. CRIM is an applied research center located at the crossroads of the academic world and the industrial world. It brings solutions to AI problems of the companies using the state-of-the-art knowledge coming from universities. And its strengths like in its theoretical expertise and practical know-how, and in its deep knowledge of industrial problems and constraints. So we generally work with companies, but we also work with non-profit organizations. And as a project we present today was realized with the Broadcasting Accessibility Fund and with the support of BANQ, OQLF, and other non-profit organizations. So the project aims helping visually impaired people to enjoy films thanks video description. So what is video description? It's a text written by a human video describer, and it's read by a synthetic voice. It describes what is happening in a visual scene to enable people with visual impairments to understand the scene and to enjoy the films. VD is usually inserted between dialogues. So some action are described just before they really happen on screen, and some other are described just after their apparent screen. So this can create some alignment problems between the visual actions and their description, as you can see in the example on the right. Over the past 20 years, CRIM has built up a solid expertise in video description, not only by describing more than 140 films or TV series, but also by designing and producing video description tools such as scene detectors, character recognizers, speech detectors, etc. So until now, video description texts are produced manually. And this is a very time-consuming task, which is a barrier to universal accessibility. But recent advances in machine learning demonstrate great potential for automatic generation of video. This implies two steps. The first one consists in recognizing visual elements in a video. So the scenes, the localization, the characters in the scene, and the actions performed in the scene. The second step consists in composing the video description, that is, writing the text of the video description. So once we have all visual elements from step one, the text generation could be done through automatic text generation. But in French, resources for automatic generation of video description are insufficient, not to say non-existent. So our goal in this project was to create a dataset in French for this task. And from our precedent work, we already have information about scenes and characters appearing on screens. So our contribution today consists in the annotation of the action in each scene and the production of a unified and rich dataset bringing together all these elements. So the outcome of the project, I said, takes the form of a unified dataset that we've called FrVD, containing for each film or TV series the video clip references, the corresponding video description, the metadata of characters and actors and of scenes, and linguistic annotations of the video description text, and the action. So the action inferred from the video description, so from the text, and the action inferred from the video. And both are using the same vocabulary called AVA. So in the following slides, we will present how we obtain the linguistic annotation, the action inferred from the video description, the action inferred from video, and we will show you our analysis and visualization tool. So let's begin with the linguistic annotation. We first used SansDA from Stanford University to automatically split the text in sentences and tokens, and then to tag each token with its part of speech and its lemma. To detect the action expressed in the video description, we proceeded in two phases. In the first one, we've manually annotated 45% of the corpus. In the second one, we've trained a BiLSTM CRF tagger on the manually annotated corpus of the first phase, and we've used it to automatically tag the rest of our corpus. So what did we tag exactly? We tagged actions denoted by a verb or a light verb plus a predicate. And we've tagged the entities involved in the action, that is the subject, and the objects, direct or indirect. So let's look at an example. Here we have a sentence of the video description. Mirabella se retourne et aperçoit Brad prenant des notes dans un carnet, meaning Mirabella turns and sees Brad taking notes in a pad. So, and we see the different annotation levels. So the token, the lemma corresponding of the token, the span of the token, the part of speech of the token, and the action annotation in the IOB format. So we have here a subject and here an action representing by two tokens, another action and an object. So it was important for us to indicate the type of the subject, if it's a human, an animal, or inanimate, because our aim was to detect action performed by people. So as a result, in our corpus, more than 26,000 actions were detecting, including more than 23 actions with a human subject. This represents a total of almost 9,000 unique actions. So the diagram below shows the frequency of occurrence of each action in descending order. So it's a beautiful Zipf's distribution. The main actions are very frequent, but we also have a long tail with a lot of rare actions. And it's interesting to note that the 300 most frequent actions represent more than 50% of the total number of actions. So now I will let Francis explain you how we infer the actions from the videos.
Yes, thank you. So because the actions can be annotated in the text before or after they actually happen in the scene, we have to use a visual model to infer what happens at a specific time. So in our project, we decided to only apply. We are not training a full model. We just use what is available in the state of the art. So the first step was to basically pick which state-of-the-art model we're going to choose and on which data set we're going to produce results. So when we looked at, for example, on papers with code, we saw very fast that the model SlowFast by a Facebook AI research lab was one of the most the highest rated in terms of prediction accuracy. So it was an obvious choice. We stick with SlowFast. And we had after to choose which of the available data sets should be applied. So there's Charade, Kinetics, and AVA, for example. Next slides, please. So SlowFast is a very brief summary. It's the general idea of it is that you have two branches on each. One is the fast and the slow, and each one process frames at different intervals. So basically, in order to consider the fact that some action take a long time, like walking, that could take a few minutes, and jumping would only last a few seconds, if not less than a second. So in order to detect both these kind of situations with very different time frame, it's important to consider both aspects. So each branch will process images in a different method. The slow branch will skip basically multiple video frames and analyze in higher resolution each one that is being processed. And the fast branch does the opposite, process almost each frame, but at very low resolution in order to process more of them. And there are lateral connection between the two branches in order to synchronize the spatial temporal information. So the next step was to pick which data set we're going to use as our lexicon for our actions. So the first three choices that came up was Kinetics, HMDB, and AVA. We noticed that Kinetics with 400 action is, in our opinion, too often precise. There's a lot of action that have extremely low frequency and that were basically almost never appearing in our cases for videos. So we decided to not stick with it because even basic cases that, like Lise said, was 50% of the action we were expecting were not even available. On the other side, the HMDB dataset has 51 actions, but it's very specific to actions related to sport events. So like throwing, push-ups, sit-ups, and stuff like that. And we didn't find these actions were happening that often in some specific movies that didn't have anything to do with sports. So we found this dataset to be too generalistic. We stick with the AVA dataset, which offers 80 actions, and it's a good middle ground between generalization and precision. Some of the actions are represented in the table right there. So we have the general actions such as sitting, standing, walking, but we can have often more precise action with answering phone, for example, or fishing, which will be more specific to a very specific activity. So from one side, we saw that the text part had a lot of specific verbs that were extracted from the video descriptions. And on the video side, we stick with the AVA actions, but there's clearly a mismatch, both in terms of language and number of action. So how are we supposed to validate the video actions that are produced by SlowFast against the annotations that we have on the video description. So there's a need to create some kind of alignment and mapping between the two domains. But to do so, we had to consider a few challenges. First, like I said, there is a difference between which actions are represented on each dataset. And there's also the difference of language, which requires some extra conversion of language and translation. There's a very important distinction in domains that needs to be considered also, mostly because in the text we can see that annotated action usually represent a verb in a sentence, but these verbs come with other semantic rules and other association with other words within the sentence that describe more specifically what is happening. There's a nuance that these words can apply to the verb that will change a bit the meaning. And there's also a large number of synonyms that can be applied to say a similar action. So it's important to consider all these kind of synonyms as similar representation of the same action that could be represented in the visual word. On the opposite, in the video, detected actions are very generic physical activities, gestures, or movements that are very specific to the visual attributes. So verbs that are not easily represented with visual aspect are rarely described. Also, there's actions that are accomplished in the AVA dataset are often, if not always, in relation to a character and sometimes objects. So some more abstract verbs that could not be associated to a character or objects are often not represented. And finally, actions and interaction between all these items are annotated in different way. Usually they follow the semantic of someone, verb, something. So it's important to consider these kind of representation versus the IOB, for example.
So I'll now explain how we mapped this 9,000 French verbs to the 80 AVA, so English verbs. So so to tackle this problem, we've adopted 3 different strategies: a manual alignment, an alignment through lexical resources, and an alignment through word embeddings. We applied the manual alignment on 6 films, thus creating our ground truth, our goal data set. We've also aligned manually the 300 most frequent actions, so representing more than 50% of the occurrences. Here are a few examples of the different cases we encountered. So we have here the simple case. It's a one-to-one match, so sortir means exit. And we have more difficult cases, like the 0 match. So as Francis said, not all actions are in the AVA set. For example, there is no facial expressions like sourire, meaning smile. And we have the opposite case when we have a multiple match. So regarder could be aligned with watch a person or watch TV that are both in the AVA dataset. And we also have like a fuzzy match. Rejoindre quelqu'un could be walk, but it's not a real synonym or a real. So it's near, but not exactly the same. So as the manual annotation and the manual alignment is a very long process, we've tried 2 different mapping methods. So the first one consists in using lexical resources to find the best translation equivalent thanks to the synonyms. For this, we've considered 3 wonderful resources: the Synonym Dictionary of the University of Caen in France, and 2 versions of WordNet in French, ONEF and Wolf. So our third mapping method consists in calculating the distance between the embedding representing a French action from the VD and the embedding representing the candidate AVA actions, and to select the nearest one. So we've used 3 pre-trained multilingual models that project both English and French words or expression in the same vector space. So Muse, fast text, and sentence BERT. The hybrid method combines both of the manual and the automatic alignments, choosing the automatic one only for rare actions, and the most frequent ones being covered by the manual alignment. So this constitutes our silver dataset, that is a ground truth approximation. So thanks to our gold dataset, we try to evaluate the action inferred by slow fast. As a metric, we chose a recall at 5. As you can see in this table, the performances are quite low. So we have for the 6 gold films a recall on 21.6%, and for the 300 most frequent action, only a recall of 17%. So this can be explained by many factors. So first, as said before, the VD is not always perfectly synchronized with the action it's described. And as said before also, the video does not aim to describe all action, but only the ones important for the plot. So it could be an action like lost in the middle of other activities on screen. And finally, the Have Action Chat was not designed to describe a film, but to describe short YouTube videos with a single plot, and some important actions are missing. So our dataset, the FrVD dataset, offers a multitude of possible research possibilities, either on computer vision or in NLP. So, as a summary, the FrVD dataset contains a JSON file per video, gathering the different elements we presented today and some global metadata. It's a very rich resource, and Francis will show you now a sample of this dataset, and the tool will provide open source to analyze it.
So I picked the movie called Bon Cop, Bad Cop as an example. So we can see that at the start of the file, there is some metadata related to when was the file produced and other general information to retain its provenance. So it's easy to trace back where the annotations came from. And then it's followed by other metadata related to the actors, the characters, the scenes, and all the video annotation and textual annotations. So in each case, we have some unique IDs that are generated. So even though we have different characters in movies, they are sometimes represented by same actors. So it's possible to associate them between movies and do some tasks such as face recognition or whichever association we want to use visual attributes. It's possible also to see that scene IDs are replicated across each video description entry that will indicate basically where some actions are happening in the movie. So all these information are available and can be analyzed as needed. As we can imagine, the whole data set with 142 videos and video description entries for each small time interval creates a lot of metadata. So we had to create a tool to analyze it and visualize it. The main challenge of the tool we had to resolve was basically the desynchronization between the multimodal actions. So the text action are perfectly aligned with the visual description because they come from it, but the video actions are aligned with what actually happens on the scene, which is not necessarily at the same time as the video description. That could be before and after. So the tool attempts to solve some of these cases. It also parses the generated metadata files for the FrVD dataset, and it renders in real time the video and the associated annotations for better analysis. So here's a sample screenshot of one video from Dans une galaxie près de chez vous, episode 14. So we can see that on the top right is the video inference results for that given scene. with bounding box detections for each character. And on the bottom right, we see the annotated text, verbs, and nouns. And in the bottom left, we have the original video description that was created by video descriptors. So in conclusion, we provide a video description data set with actions annotation in French called FrVD. We also offer a visualization and analysis tool that is open source. And we provide some automatic labeling of actions for multiple baseline algorithm as it was presented by Lise. We consider that the provided FrVD dataset will offer future research opportunities, such as the analysis of correspondence between visual and video described actions. There's also possibilities into analysis of the relevance of action. So whether more precise or more generalized action will provide better results. The analysis to improve the prediction based on context. So in our situation, the actions were produced only based on what is seen at a given time interval, but including some contextual information such as the scene, the position of the characters, objects in the scene could improve predictions. And finally, which was the goal of the whole project, is to help into improving automatic text generation of video description and the semantic classification of actions. Thank you.
Thank you very much for your great presentation. So we have about 8 minutes for questions from the audience. So you can use the raise hand option in order to virtually raise your hand, and I can pass the microphone to you. I can maybe start with the question from myself. So on slide 6, you mentioned that you manually annotated 45% of the data.
Yep. Yes. Sorry, I can't hear you.
You can't hear me? Can you hear me
Yes,
now?
yes, now I can hear you.
Okay, yeah. So you mentioned that you used 45% of the corpus. You did it with manual annotation, and it was 34 days of annotation.
Yes.
My first question was that how many annotators did you have?
We had one main annotator and one spare annotator, so 2 annotators.
I see. It's quite like a lot of effort in my point of view. So my first question was that did you find this amount of work at the bare minimum that would be required to come up with the weak supervision approach to annotate the rest of the data, or did you just pick this was the amount that you just did for that part, and maybe someone could settle for lower amount of work? And my other question is that, like, is there any way we can maybe if we want to expand it for other languages, is there like approaches, do you think of any approaches that could be used in order to have this process faster and reduce less amount of annotation?
So as a weak supervision, we're using like the part-of-speech automatic annotation that help us as annotator to find the verbs and the nouns and so the appropriate subject and objects. But then, yes, we took this whole corpus, also data set as a training corpus to tag the rest of the corpus. And we had a precision, I think a F1 measure of 80% of for the rest of the corpus. So it was a sufficient result for us. So we haven't tried to train with less data and compare the results. So perhaps we could have avoided spending so many days. Perhaps only 20 days were sufficient, but we haven't tried it actually. So
Yeah, I was mainly asking for future references if someone or some other team wants to spend some time and creating the similar data set but for a different language. I just wanted to know your experience on it and in order to make it more efficient. Thank you very much for your answer. Dr. Dishulo has a question. Dr. Dishulo, you can unmute yourself and ask your question.
Yes, thank you for this presentation. It reminds me when I was at CRIM and a lot of time, past time ago, and it's very interesting. I had a question. Are you sensitive? Is the system sensitive of aspect of what is seen, which is outside of argument structure? I mean, do you also try to capture the presentation of the event or some kind of modality or modification of how the events goes about and all these things that are seen, interpreted, but beyond argument structure, like subject and object, so-called, like quantification, or modifier of intents or things like that, of intent or like intensity of the action or things like that.
Yeah, there will be two elements in my response. The first one, the video descriptions tries to be the more objective and to be not subjective and to describe exactly what happened on screen and not giving like the sentiment of the emotion of the video describer. But we have also attributes on our annotation, like is there a negation or is there like a verb tries to do? So we have this kind of annotation, but we haven't used it in the rest of the project, but it could be fine in the data set.
Yeah, so I wasn't talking about interpretation and sentiment. I was trying to say, someone can walk or run. Someone can walk slowly, fast, but not run. So I was meaning a manner of presenting, of seeing the event going on, right? So which is like peripheral somehow to the argument structure. But of course, subject and object, everyone knows they're around, right? So, but then if the analysis would go beyond that in, expressing, some property of the event, which is also what we're seeing. We're seeing, let's see, two people, a subject, an object, someone does something to some other one, but maybe describe it also the way that the event unfolds. I don't know.
So we haven't annotated it. It was outside the scope of the project, but it's an interesting case. But so the video describer have to write short text.
Yes.
So they have to find a verb that really express what happens on the screen. So and they prefer to write so to avoid using like adverbs, but to find a verb that. But yeah, we also find adverbs and some circumstances in the sentences, but it was outside the scope of the project.
Yeah, it's interesting.
Thank you very much. We can have time for one quick question. If we don't.
Maybe I can ask you a question if I have the time.
Yeah, sure.
Yeah, this is Jamie. Thinking about a kind of evaluation problem. Suppose that you want to use your data set to train a model and to generate some description from a scene. Then the question is, how are you going to evaluate your system? And that seems to be quite complex, and it reminds me something like document text summarization. So when you have a text, you have different ways to summarize the content. And here, maybe you have a similar aspect. That is, you can have different ways to describe the scene. Then there is no unique way to describe that. So I'm wondering what do you want to do with the data set that you created? Suppose that you want to generate the description. How are you going to evaluate the performance of your system?
Yeah, it's a very good question, and evaluation is always like a challenge in itself in so text generation. And so there are some new metrics now. So the old metrics like Rouge could be used, and if we have many video description for the same videos, it could be useful also. And you have also like metrics like Meteor and so on. So, but I think so. This area needs more research, and we focused only on action, so expressed by a simple verb. So it's a simplification of the task. But if we want to produce real sentences and real video description, so yes, we have to think deeply on how we evaluate it.
Okay, good. Thank you very much. I think we can move on to the next talk. Thanks again, Lise and Francis, for your great presentation. Our last speaker is going to be Tanmay Gupta, who is a research scientist at Allen Institute for Artificial Intelligence, and his presentation title is Towards General Purpose Vision Systems. So without further ado, Tanmay, the floor is yours.
All right, thank you. Are you able to see my screen and hear me all right?
Yes.
Okay, perfect. Okay, thanks for the invite. My name is Tanmay Gupta, and I'm going to talk about our recent work on Towards General Purpose Vision Systems. This is work in collaboration with Amida Kamath and Ani Kemavi at AI2 and Professor Derek Hoyam at UIUC. Right. So the state of computer vision today consists of single-purpose models and multi-purpose models. An example of a single-purpose model would be an image classifier trained on the ImageNet dataset. Now, we have obviously been making progress on many such tasks, but such models are able to do one and only one thing really well. And making a small change, for example, just changing the number of classes or training it on a different data set might require an architecture change, such as replacing the last layer, last classification layer in your CNN. Another example of a single purpose model is monocular depth estimation. So the models have progressively gotten better at producing better and better depth images, but they can only do depth prediction and nothing else. On the other hand, we have multi-purpose models. A popular example of this is mask-RCN, which can do detection, instance segmentation, and key point prediction. And these models can obviously do more than one thing. But at the same time, these tasks are pre-selected and fairly limited in the number. So one way that this pre-selection manifests itself in model design is, for example, in vision language models, you might have a task-specific output head. And even data sets which have, even data sets for the same task like VQA and GQA would have different output heads to model the different answer distributions. So to summarize, the state of computer vision today consists of n-purpose models. N is equal to 1 for single purpose and n greater than 1, but still pre-selected and small for multi-purpose models. And this means that it is difficult to scale a system that is built for n tasks to n plus m tasks or m new tasks. And even adding one new task requires non-trivial modifications to the network architecture, for example, adding a new output head or changing the training process. by adding a new loss, etc. So our goal in this work was to go from end purpose to general purpose. And the difference is that in general purpose models, n is large and unknown at design time. So for end purpose models, the system is expected to only handle certain set of predefined tasks. In general purpose, the system does not know what tasks the end user might care about. And so the design has to take into account the fact that the model is expected to see new tasks. So a question that might come to your mind is, how are general purpose models different from the so-called foundation models, which is a recently introduced terminology? An example of foundation models are CLIP, DALI, BERT, and GPT-3. And obviously, these have shown impressive performance and even emergent properties like few-shot generalization in case of GPT-3. But let us put a pin on this for a second, and we'll get back to this question towards the end of this talk. So now that you know what the broad motivation of GPV is, let us dive a little bit deeper. So we define three tenets of GPV, and these are sort of guiding principles and yardstick for measuring progress towards this grand goal. And these are generality of architecture, generality of concepts across skills, and generality of learning. So the first tenet, generality of architecture, means that a general purpose architecture should support learning a wide range of tasks within a broad domain without requiring any change to the architecture or learning algorithm. And the inspiration for this comes from biological general purpose systems. So for example, us humans, we have very limited number of inputs, right? The 5 senses. And we have very few outputs as well. So we have limbs for locomotion and manipulation of our environment, and we have the ability to synthesize sound. But given these limited number of inputs and outputs, we're able to handle an astonishing range of tasks in the real world. And note that we don't need to sprout a new head or a new limb in order to learn new tasks. And even animals like lizards and octopus, which do have the ability to generate body parts, don't keep on sprouting new limbs and heads over the course of their lifetime. So another motivation for trying to strive for this is the sweeping success of encoder-decoder architectures in NLP, where this fairly general architecture has been shown to perform really well on a wide range of NLP tasks. The other thing to borrow from NLP is recent work on learning from task descriptions. What I mean by learning from task descriptions is things like T5, where you feed in templated task descriptions. So you could say, translate English to German and the phrase that you want to translate, and the model understands the task that it needs to do, and it outputs the German translation. Or you could say, summarize and in a long passage, and the model understands that you're asking for a summary of that passage. On the other hand, you also have full-fledged natural language task descriptions, where you might feed in instructions which are significantly more complicated. Essentially, what you would feed to mechanical Turkers in order to get annotations for your dataset. And learning from task descriptions has a few important advantages. So first of all tasks simplify to encoding and decoding a sequence of text tokens, at least in the case of NLP. And what that means is that a fairly task-agnostic architecture is able to support learning a variety of tasks. And the other big promise of task descriptions is zero-shot generalization to novel tasks, which means that you train it on a bunch of task descriptions and different kinds of tasks. And at test time, you expect it to generalize to a task that it has never seen, but is expressed in natural language. So here's what one potential solution for GPV may look like. We could specify tasks using natural language prompts and equip our model with a small number of modality-specific output heads that are reused across tasks. Note that here we're talking about modality-specific heads instead of task-specific heads. To give you an example, let's say our model was equipped with the following 4 output heads. So we have the ability to produce text, bounding box, region relevant scores, which are scores for these boxes, and images. We'll be able to do a wide range of tasks. So for example, classification could make use of the text generation head. VQA and captioning can make use of the text head for producing the answer or caption, and the box and relevance heads for producing an attention map, which is interpretable on the image. Object localization and referring expression can use the box and relevance heads. And tasks like depth prediction, semantic segmentation, and instance segmentation, and even image-to-image generation would be able to use the image generation head. In this work, we have focused on this highlighted region. So we don't currently have an image generation head in the model, but this is something that we are working on. So this is what the architecture of GPV1, our first installment of this architecture, looks like. And at the higher level, we have encoders for vision and language and decoders for vision and language. So the vision encoder consists of a CNN backbone followed by encoders, transformer encoders and decoders from DETR. So those who are not familiar with DETR, it's a transformer-based object detection model. We have a language encoder that is used to encode the task description. And here we have used BERT, which is a little bit old, but you get the idea. The features that are produced by the vision and language encoder are then fused using Wilbert's co-attention layers. And these are fed into a text decoder to generate text and the vision decoder to generate bounding boxes and region relevant scores. So note that I told you what the architecture is, but I didn't tell you what this architecture was designed for, right? And which is exactly what I mean by the architecture being task agnostic. So to prove that point, we jointly trained this model on 4 tasks: localization, categorization, VQA, and captioning. Each mini batch would consist of a mix of samples from all these tasks. And the other trick that we had to use was to initialize the vision encoder and decoder with pre-trained DETR weights. But once you do that, we're able to fine-tune the entire architecture end-to-end. In terms of the losses, we only have 2 losses to support these wide range of tasks. So things that provide bounding box supervision use the Hungarian loss. So for example, localization. And tasks that provide text supervision, like categorization, VQA, and captioning, we use the negative log likelihood. So we maximize the log likelihood of the ground truth text. So to give you an example of the kinds of questions our model is able to handle, you can ask things like, what color is the dog? Are there trees being seen? Which are VQA questions. And the output consists of, obviously, the text answer, but we're also able to produce relevant scores for boxes. And they're quite meaningful, actually. And note that VQA does not provide supervision for bounding boxes. So it's learned purely from the localization task, but it generalizes in case of VQA. We are also able to handle localization queries like locate the dog or find the dog. If you ask generate a description for the image, it produces a caption. And if you give it a crop region and ask what is this, it produces a class label. So we have an online demo, and you can find it here. So by the way, this entire talk is recorded, and it is available on AI2's YouTube page. YouTube channel. So if, let's say, you want to revisit that, please feel free to do that. So that was the first tenet, which is generality of architecture. Now let us look at the second tenet of GPV and my personal favorite, which is generality of concepts across skills. So this tenet says that a general purpose architecture should be able to perform tasks in skill concept combinations not seen during training. And to understand that, we need to understand this idea of skill concept factorization. So let's say I have a bunch of images of dogs and I have questions about dogs, like what color is the dog? What animal is this? Is the dog furry? And let's say your model is able to answer these questions correctly. So we might say that a model possesses the skill of VQA for the concept dog. Similarly, if you have images of cats and you're able to localize cats, so you're able to handle queries like find cats in the image or localize the white cat, then we might say that our model possesses the skill of localization for the concept cat. Now, in skill concept factorization, we ask the question, given that the model was trained to localize cats and answer questions about dogs, can it handle the other combinations? So can it answer questions about cats and localize dogs? And that is exactly what we mean by generalization of concepts across skills. So to test this, we collect the COCO ski dataset, which is essentially a new split of COCO to test generalization of models on novel skill concept combinations. And it consists of these 4 skills that we train a model on: classification, localization, captioning, and VQA, and consists of 80 concepts. But the interesting thing about COCO's key is that in order to test this novel skill concept combination, we hold out certain skill concept combinations during training. So for example, this first subset of categories in COCO are held out from the VQA and captioning dataset. Note that they are visible in the classification and localization training data, just not in context of VQA and captioning. The second subset is held out from classification and localization. And then there's a last subset, which is shared across all tasks. So the model might see these categories in context of any of these 4 tasks. So now let us look at how our model does on this benchmark. So we are going to report performance on these 4 tasks: VQA, captioning, localization, and classification. And we'll report 3 things for each task. Test refers to the performance on the full test set for that task. Seen refers to performance on the set that does not contain any of the held out categories. So it's a subset of the test set. And unseen refers to the subset of the test set that mentions any of the unseen categories or the held out categories for that task. So to establish a baseline, we evaluate specialized models like Wilbert for VQA, VLP for captioning, FastRSN for localization, and Resident 50 for classification. So each of these models is trained on the COCO train set for that task. And note that these are not multitask, right? So each of them is trained only on one task. And even in case of specialized models, you would see that there's a significant drop in performance from seen to unseen. And then we report performance on one task GPV1. So this is GPV1, which is trained on each of these tasks individually. So it is not doing multitask training yet. And you see that the performance is roughly the same as what specialized models get. Maybe there's a little bit of difference here and there, but for the most part, it's very comparable. Note that classification unseen gets 0 performance because if you train it on, let's say, 70 of the 80 COCO categories, it has no way of classifying the remaining 10. But then when we do multitask GPV1, so this is GPV1 trained on all 4 tasks simultaneously, we see that the performance improves quite a bit, especially on unseen categories. And this is exactly because of skill concept transfer. So the categories that were missing from the classification training data are now being provided supervision for in VQA and captioning training data. Okay. But note that a significant gap still exists between seen and unseen, and there's a lot of work that we need to do to bridge that gap. And finally, we provide an oracle. So this is GPV1, which is trained on the original COCO train set. So it sees both seen and unseen categories, and it provides a loose upper bound for what we would expect if we were doing skill concept generalization completely. So here's the last tenet of GPV, which is generality of learning. And this says that a general purpose architecture should be able to learn new tasks with minimal loss of performance on previously learned tasks. So there are 2 core challenges of this third tenet. The first is sample efficiency, and the second challenge is learning without forgetting. So to test this, we do an analysis on the reference expression dataset. So essentially what we do is we train GPV1 either only on the localization task or on all 4 tasks, which is the multitask GPV1, and we evaluate its performance on the referring expression task in a 0-shot manner. So each of the referring expressions becomes a prompt or task description, and we just see what are model outputs as bounding boxes for these queries. So clearly, multitask GPV1 does significantly better on the 0-shot task analysis than GPV1, which was trained only for localization. And note that the difference between localization and referring expression is that localization might ask you find the dog, whereas referring expression would ask you to find a specific dog. So maybe the dog on the right, or here in this case, the dog with red across nose. But obviously, there are errors in the 0-shot setting. But as soon as we start fine-tuning this model on referring expression data, these errors are quickly fixed. So here we report performance as we train on more and more referring expression training data. So the blue curve here is as we fine-tune GPV1, which was pre-trained or trained only on the localization task, and the orange is multitask GPV. And we see that multitask training improves sample efficiency. The dotted lines here are zero-shot performance, and there's a significant gap between multitask performance and single task performance in the zero-shot setting. And finally, we do this analysis on to what extent are our models retaining the past performance. So as we train on reference expression training data, we look at the percentage of performance that was retained on existing tasks. So all of these solid curves show the percentage of performance that was retained on one of the 4 previous tasks that were learned. And the dotted curve is specifically showing the percentage of localization performance retained when you fine-tune GPV1 that was trained only on the localization task. And here again, we see that multitask training improves retention of old task performance. All right, so those were the 3 tenets. Now back to the discussion of foundation models in vision. So we have impressive models like CLIP and DALI, and we are often impressed by how well these generalize to new data sets. But we have to remember that these are still very specific models. So for example, CLIP can only do image text matching, and DALI can only do text to image generation. And they're really good at it, and we are learning more about these models. But these are not quite there in terms of being general purpose yet. So the relation of GPVs to foundation models, at least in our viewpoint, is as follows. So foundation models might provide representations of images and language that would be useful for GPVs to build on. But at the end of the day, we expect general purpose vision to lay the foundation for the next generation of research in computer vision and NLP. And of course, the emphasis on the 3 tenets is also important, because we do want a more general architecture that allows people from a variety of domains to use these models without requiring special training. We do expect our models to learn concepts from certain skills and then be able to apply them to new skills and so on. And we expect our models to learn efficiently and without forgetting. So with GPV1, hopefully we have made quite a bit of progress, but there are many limitations that remain. So first, we do not have an image generation head for tasks like depth prediction or image-to-image translation. So we do need that. We do not have an explicit mechanism for handling forgetting. So we did show that multitask training brings you some robustness to forgetting, but we do not handle it in any special way yet. The model is difficult to train from scratch, so the vision encoder and decoder needed to be initialized with pre-trained DETR. And if you have trained DETR yourself, you know that it's a very expensive process and takes quite a bit of time. And overall, the compute requirements for GPV1 were quite high. So we required 4 Titan RTX, 24 GPU memory each, or one A100, which has an 80 GB memory, and the training time was 5 to 7 days, depending on what tasks you train on. So the key takeaway messages from this talk are the following. All vision models today are n-purpose models. The system is expected and designed to only be used for a small number of predefined tasks, and we hope to make the leap towards general purpose vision, which is design systems that are expected to encounter and adapt to a large number of new tasks within a broad domain. We talked about the 3 tenets of GPV, which we believe are good guiding principles in this pursuit of this grand goal. And we created GPV1, which is a task-agnostic vision language architecture as a step towards this goal. So GPV1 can take as inputs image and task descriptions and output bounding boxes with relevant scores and text. So with that, thanks a lot. We have our demo qualitative results and code links here, but you can also find them on our project page.
Thank you very much. Very exciting presentation. It was great to see the work that you have done at AI2. Do we have any questions from the audience? We have 10 minutes for the questions. And as for the previous talks, you can use the raise hand option to ask questions. Dr. Sciullo, can go
Yes.
ahead.
Thank you for this presentation. It was interesting. I liked the idea of generality of across the board. So I have several questions. For example, how similar is vision from language, which is a basic question. And a more specific one is, can you do this with like motion, like a video, and translate it to a natural language? Or do you do static image, or can you do dynamic images?
Okay. Yeah, so let me take a second question first. So currently we do static images, but we do hope that as we become more and more general, we'll be able to handle videos as well. And we do have an intern who's working with us on trying to use this architecture for video tasks. So video captioning, video Q&A, and things like that. And with respect to your first question, how different is vision from language? So I think once you are able to encode an image into what the objects are, where they are, and how they're related to each other, and your output is a text or a bounding box, it is very similar to how you could think of natural language tasks, right? For example, natural language translation or classification of sentiments and things like that. It is basically a token-to-token task. The problem here in vision is we do not have those discrete tokens that natural language naturally provides, right? So for example, it's very difficult to discretize an image region into a token, let's say token 7 or token 30 or things like that. So that is where the challenge comes. But a lot of people are actually working on doing that. For example, DALL-E is able to discretize an image into a grid of integers. And then you can use that as a token for translation.
Mm-hmm. Can I have a follow-up question?
Yeah.
So, you know, there are theories of language saying that, in fact, what the language, a specific property of language, it's to use a function that generate structure. And then the externalization of the structure is something else, is something that is accessible to the sensory motor system. You can hear it, you can read it, but what you read or what you hear from language is not the abstract generation of relations that the mind computes. So, of course, this is a different approach to the different human capacities. You know, you can see an image, you can talk about the image, etc., etc. Mm-hmm. And moreover, learning these things is based on exemplars, right? Learning on the basis of exemplar. Do you think there is any chance that at some point research can be done on relating the computation of the brain to language and what the brain does for vision? Okay, there's theories about that too. Marr is one of the famous scientists who proposed a theory of vision that is very specific. And so I would look into the pages that you did and seek for some kind of interaction between these two things, because if you generalize across the board, you might miss the specificity of each thing you generalize upon. Mm-hmm. It's just, yeah, that's a comment on your answer to the question.
Yeah, no, certainly that makes sense. So we do, for example, understand that as you make things more and more general, you lose some advantage of special purpose systems. So for example, detection, the way faster RCN does it is really, really efficient because it encodes certain characteristics of the problem, the structure of the problem. And when you do general purpose, you lose a bit of that. But at the same time, general purpose brings its own advantages, which is what we are excited about.
Yes, so there's a great progress in image recognition in machine learning, right? Mm-hmm. But the progress in NLP is slower to come, right? One might think that maybe with image, you can calculate exactly the position and the properties of the image in mathematical terms, higher mathematical terms, and characterize effectively a picture static or in motion, which is not always, it's not the case for NLP.
You mean like NLP does not have this grounding to the physical world?
There are recent research suggesting that higher level mathematics has nothing to do with language, which uses a lower kind of mathematic because of mind limitation, the memory space and the capacity. So you have limited resources. The brain has limited resources for human language. And the kind of mathematical approach that has been taken in machine learning, rightfully, because it's, mathematics and, computer science, might be something that is very good to discrete objects, like images that you can, identify the dimension and calculate, but maybe it's, it might not be what is there in human language. So my take on this is that new research would take into consideration might be different kinds of object you want to treat with machine learning, and what is the best method to treat each one. Is really vision like language? It's a fundamental question, I think. So just a comment, right, biased comment. Yes.
Thank you very much, Dr. Sciullo, for your question, and Tanmay for answering the question. So do we have any other questions from the audience? We have one last question. If not, I guess there are no more questions. Thank you very much again, Tanmay, for your very exciting talk.
Yeah, thank you.
Thank you for joining the presentation. And so we have reached the end of today's Meetup event. Thanks everyone for attending the Meetup, and thanks to all the speakers for their very exciting presentations. Please follow up on the website and check for the upcoming events in terms of meetups and the workshop. The link to the website has been posted in the chat by Guillaume. So if you want to know and stay up to date with the upcoming events, please don't forget to check out there. And the video for today's meetup will also be uploaded on the website, so you'll be able to see it there once after the meetup. So that would be it. And thank you again, and I hope everyone has a great rest of the day.
Thank you. Bye-bye.